All right, this session is my complete grab bag session. Okay, there are SEM tools that are worth being familiar with that we have not covered in detail yet, as well as some parts and basic bits of operation that I left out of the other stuff. So this one is to cover all those things, making use of the time we have. But if you don't care about one little detail of this and you would find more value in practicing on a device, great. This one is whatever you need it for. Okay? So first, we've had 3.5 days of this. Does anybody have anything they want to ask, anything they want to make sure we go over that we haven't covered yet? I will throw the floor open for discussion. Please do use the microphones if you do. Nothing. All right. So we've covered a fair amount of how stuff works inside an SEM, but there are some details and basic operation things that I thought were neat when I was looking through these, but spending time on them on Tuesday was judged not that valuable. So those are what we start off with. Who's excited by vacuum pumps? All right. So most SEMs have 2 types, possibly more, of vacuum pumps. And it is absolutely required to have a vacuum on this system at some level. Because if I try to fire an electron beam at any of you right now, I will fail. It will get absorbed by the atmosphere, and I will ionize the atmosphere, and it will just not get to you. Okay? Also, if I try to fire electrons from a tungsten or crystal filament and there is oxygen running around, well, significant oxygen is bad for things that get hot. Gas molecules also can interact with the surface of a sample, obscuring detail and lowering contrast. Okay, most systems, when you plug something in, you open the chamber, you insert your material. There are 2 pumps that operate. You might call them a roughing pump and a turbo pump. This is one of the plausible designs for a roughing pump. I kind of liked it. It was kind of cool to think through how this was engineered. Okay, so here's the sample chamber with a spinning device here. As this spins, this volume basically kind of, you're creating a wind pulling away from it. And this part under here, you're getting put in compression. So as this spins around, this part gets put in suction every loop. This part gets put in compression every loop, and that lets air in and then pushes it out every step to a certain extent. That's an example of a roughing pump design. Turbo pumps are kind of fun. These are basically jet engines. I liked finding the design of these. It is literally spinning rotors with angled tips, and the angles on the slots are designed so that as gas molecules hit them in a low vacuum environment, they get momentum impelling them in a single direction. So it literally is like the blades in a jet engine firing stuff out as single individual atoms or molecules of gas being fired out. There are many other designs of vacuum pump. Those are 2 standard ones. There are cold traps that can be used as vacuum pumps if you need to get something out through keeping it cold. There are sputter ion pumps that are commonly used in the electron guns themselves to keep the guns at particularly low pressure, which is an ionization tool that ionizes the gas and then locks that gas away by using a magnetic field. Gas molecules sticking to a heated metal surface. There's a variety of these as well. Hopefully you can see why we didn't spend our initial time on this setting up, because they may be kind of cool. You don't exactly need to know this to operate an SEM. Next on my list, it's called a scanning electron microscope, right? How does it actually scan? Seems like a valid question to address. Okay. The actual process that went on every time you looked at an image in there is we have our electron source. We have our set of magnets that do several things. They bring it into focus and also accelerate the beam at the anode. We have things that are built in as corrections for stigmation, for beam, suddenly blanking on the term. I mentioned it was literally in my lecture on Tuesday, and now I've blanked on it. The spherical aberration. There it is. Thank you, brain. Am I fried? Do I need more caffeine? Apparently, I need more caffeine. There is one other set of coils in there, which are the scanning coils. Hi, Alan. Okay. In order to make an SEM actually scan, we actually have to move the beam. So there's a whole set of coils, basically electromagnets again, that have X and Y directions to them built into one of these magnets. And what does it do? In a coordinated pattern, it lays out a grid and it sweeps across it at a pace that you're telling it and a pixel size that you're telling it, or as a step size that you're telling it. So the image is only a live image truly at any given femtosecond at any given point. But it builds every time it runs through a scan, it sweeps across 1024 by 1024 and collects data at each of those. So the active operation is now here in full. We have our electron source. We have our anode that accelerates the electrons with the accelerating voltage. We then have focusing and condensing lenses to bring the beam to a focus. We have correction lenses on there that are, again, additional electromagnets. And we have something that actively controls the beam every second. And that's the thing that does scanning. So when we see an image like this, we have set some amount of pacing here. The reason we're seeing static is that we're getting scattered electrons coming from elsewhere. So an image is never perfect, especially if you do a low, short scan. This is a grating that's been put on there with a known size so that you can test the beam accuracy at something that has a known size. And it basically sweeps across there. Now, worth remembering here that if we're doing a 1024 by 1024 image, okay, and we're zoomed into 6 micrometers, well, that means that in this section right here, there's 300 pixels or 200 pixels. But the beam itself is, you can't fit 200 beam spots in there. And there is always an activation volume to the beam, which we'll talk about on the next slide again, such that there is always some overlap. This is a limitation of material science on the SEM, that you may want to be able to see something smaller than that. You may wonder why you can't get it in focus. One of the reasons you cannot get something in focus is the beam size. If you are looking at particularly small things, beam spot size will begin to overlap and beam activation volume will begin to overlap as it sweeps across things. There is nothing you can do to eliminate this. But remember, if you're trying to get a high resolution photo, and I think almost everybody in this class at some point in the last 2 days zoomed into almost maximum magnification and kind of started seeing it turn blurry. What could we do to improve that? Well, we have some tools that we can use to do that if a highest resolution image possible is our goal. The greater the beam current is, the bigger the beam is, and the bigger the activation volume is. Cutting the beam current from map to point to image to low will reduce the beam spot size. So you will lose contrast. But if you are trying to optimize fine scale imaging, cutting the beam spot size will do that. Higher energy electrons also spread out more. Cutting the accelerating voltage will again help you with your resolution and depth of field versus focus. If you are solely focusing on imaging, bring things upwards if you want to see your finest possible stuff, because if I fire a laser across the room, diffraction spreads it out as it goes. The further away from me, actually, can I do that? I can do this, can't I? Will it actually fire? Yes. There. See, as I fire across the room, the laser actually spreads out a little bit. Okay? This spot is smaller when it's closer to me than when it's further across the room. Same thing with an electron beam. I just realized I could do the actual experiment in the room. It's Friday. I'm allowed to have fun. Plus, you're all like cats following it around the room. Okay. Okay. So, move the sample up. So when we're in there, if you're looking at, hey, this thing is super fine scale. I can't see this stuff. I want to see this. Jose had a very nice looking quench texture in one of the glass grains that he was looking at earlier. But it wasn't coming in very well because each grain was sub-micrometer in scale. I only literally had like 3 minutes because I had to rush him down the hall as fast as humanly possible. How do we do the best imaging on that? Well, if we had a goal of imaging those little crystallites, cutting the current, cutting the accelerating voltage, and bringing the sample upwards, all of those would have improved the quality of any of the images. Okay, accelerating voltage. Higher accelerating voltage will give you better image contrast because the energies that will be coming back will be more spread out. And the other thing that Jose had, he had a high mass thing in there. Actually, I was asked about that, and I should mention that in a second. If we're at high mass things, they will not respond to a low accelerating voltage. So cranking up the accelerating voltage will improve the contrast. And if we are looking at high mass things and we want an EDF response, if we're at 10 kilovolt accelerating voltage, we won't get one. So it was asked earlier, did we have a polonium peak on these? We have these little beads of something metallic that formed in this glass that we polished up. It is a polymetallic phase. We got a big sulfur peak and then lots of other little ones. And at least some of the little ones were a shoulder on the sulfur peak. And that made it very hard to identify. Okay, so we scrolled through looking at what some of the peaks were. I am almost certain, in fact, the one that I have the most confidence in, we had 2 peaks that were directly associated with the L peaks in lead, which meant that this was something with some lead in it. I'm almost certain that we had a very tiny iron K alpha peak in there. And then everything else was kind of, okay, this is maybe an L peak from this, maybe an L peak from that. And nothing fit any of them perfectly. So what it probably was we had a mixture of some heavy transition metals that had gone into this metallic stuff. It was maybe rhenium, maybe osmium, maybe iridium. These are actually things that are found in some basaltic materials. We literally call them osmiridium nuggets. They have a whole bunch of platinum group elements in them. if I was actually trying to figure out what this was, I think we actually cranked the accelerating voltage up to 20 just to make sure we could get them. And, if I counted longer, it might have helped a little bit. But in reality, I couldn't actually answer this perfectly with the SEM. We had too many potential heavy elements, too many overlapping peaks. The sulfur peak that was the K peak for sulfur was overlapping with the L peaks for whatever else it was. There's a lead peak or two in there. And then beyond that, it's probably some mixture of stuff creating this set of peaks where it's gotten hard to identify. So it's probably some sort of a PGE, platinum group element rich nugget, and that's the best we could do. Which is kind of cool anyway. I mean, text and pillow basalt.
So in a case like that, if you're not 100% sure, what would be maybe the next technique to try?
We are going to go to a microprobe, and we are going to calibrate our peak position on certain elements. And then we're going to go to we're going to go back to the unknown. We're going to turn the beam on, and we're going to test whether we get an actual peak, and we're going to only count that element, okay? And once we've narrowed the peak widths in the WDS sense, so we know we're at the right peak for rhenium, we're going to look for rhenium above background and see how much above background it is. Just as a qualitative measurement, you can do this on an electron microprobe. And then we're going to test ruthenium. And then we're going to test platinum. And then we're going to test like the other 5 elements that we were looking at that could be there. And then once we've said what things are there above background, we're going to do an actual calibration. And then we're going to come back and analyze our nugget or a little bead. And we're going to see what our totals come out like. And if we're missing something important, it will not total to 100%. It will not have enough counts to account for everything that would be there, because that would mean something was doing an X-ray fluorescence and we hadn't detected it. So we need to go back in and check again for some other element that we might have missed. And even then, microprobes can often not be perfect if you're analyzing a lot of heavy stuff. So sometimes you do the best you can. And the next step beyond that would be laser ablation ICP-MS, which is quite good at measuring various low abundance elements if you can ablate a 25 micrometer area of something.
So even if you have like 5 to 10 unknown microprobes.
It's not going to tell you what the unknown is.
Right.
Unless, yes, if you have guesses, there you go. Like to do true unknowns, you would have to test 90 elements. I could rule out technetium because it does not, this was a naturally occurring Cretaceous age glass, and there was no nuclear reactors that I know of on Earth in the Cretaceous. Okay, yeah, so I can rule like 2 elements out because they're not stable at Earth's surface. But other than that, I have to narrow it down, and I could, if figuring this out was my goal of the day, I could go on peak, off peak, what is the count total? Roughly speaking, what does that turn it into if I don't worry about the ZAF correction? Is that 0.1%? Is that 1%? Is that 10% level? And then, okay, this is percent level. We'll calibrate, we'll do an analysis including that.
Is there any reason why you wouldn't say, aside from like sample disruption, is there a reason why you wouldn't just go right to the laser ablation?
I mean, they are more expensive, that too. But yeah, sample destruction is a particularly major issue too. Plus, laser ablation often struggles to do your major elements. So if you are, what will happen in your laser is if I vaporize an iron sulfide, oftentimes my iron and sulfur peaks will be completely off scale. And it will be challenging to, if I try to collect on sulfur, it will swamp out the signal of everything else. So collecting moderately present elements is okay. Like while I was at Cornell, we were doing in Esteban Gazelle's lab, laser ablation ICP-MS to identify things in monazite, which is a rare earth element phosphate. when we'd run phosphorus or oxygen, it would swamp out it would just block out the signal. It was useful because I would, for a while I was reacting things that were not correctly reacting to phosphates. So literally it was, oh, the phosphorus amount in this is weirdly 0. Okay. Versus, oh, this is a phosphate because the phosphorus is off scale. Small difference. But in terms of actually measuring the abundance of the truly major element in the phosphate, I couldn't do it. But, when we got down to, okay, this is a rare earth element phosphate, can I measure 6 different rare earth elements? Now I can measure all 12 or 14 rare earth elements and get a signal for all of them because there's 14 of the elements and half of them are low due to the even odd effect. Okay, cool. Now I can get all these on scale. That would work. But, if I'm trying to say, is this an iron sulfide? Is this a pyrrhotite structure? Can I do a sulfur to cation ratio? I can't do that on a laser ablation system. I can do that if I can get the microprobe measurement to put everything on scale. Anybody want to see an activation volume? These are done on polymethyl methylacrate. And if you know what that is, congratulations, you're more of a biologist than me. This is a material that is easily damaged under electron bombardment, meaning it has basically been destroyed anywhere that the electron beam hit it. This is basically useful for demonstrating what the activation volume in a microprobe is, or a microscope is, with a scale bar on it so that you could see it as a function, in this case, of accelerating voltage. So you're seeing it with different accelerating voltages here, where higher voltage is going to make it penetrate more deeply. And this is a 5 micrometer scale bar. This is what your activation volume looks like for your microscope analysis. If you're at low accelerating voltage, you get that thin little area. As accelerating voltage or current goes up, it becomes this bell shape. So when you're doing an EDS analysis on a mineral or a glass, what area is actively spitting out electrons and X-rays back at you? It's something like this. Why do we then have to worry about absorbance? Because your electrons and X-rays have to go through that path to get out. I did like that and didn't have quite enough time to show that. So why was this drawn like this? Because you can do experiments on plastics to verify what your activation volume is like. So the electron beam comes in as this sharp thing, spreads out through your sample. And now you get coming from right here, Auger electrons, you get coming from some volume, secondary electrons, you get coming from some other volume, continuum, X-rays, backscattered electrons, and so forth. So if we're thinking about this at the highest detail that we might want to, is the activation volume for backscatter the same activation volume as for secondary? No. There is complexity at every level. This is not a simple analysis in a chemical sense or in a high energy physics sense. So if you're ever wondering about something weird in your analysis, these are things to stick in the back of your head, okay? Why am I not able to get a single element? Why am I getting bleed through from one mineral into the next while I'm doing an EDS operation? Why does this boundary look fuzzy? The boundary may look fuzzy. The sample volume may be hitting other stuff because of the amount of interaction types that you're getting. Other terms worth adding here, elastic and inelastic. An elastic interaction. An electron interacts with a much more massive nucleus of an atom. Very little loss in energy happens from the electron because this is our billiard ball setup, where if I have a massive nucleus and an electron, bounces. if I have two electrons that come in, they interact and exchange energy inelastically because they have about the same mass. This is the same terminology that's used in neutron spectroscopy or many other types of spectroscopy where you have elastic and inelastic actions. So here's the full plot of this that I showed you earlier. We're firing our electrons at the sample. Some electrons return with virtually the same energy we saw coming in. Those interacted with the nucleus. What are those? The backscattered electrons. Note that there are a variety of energies that still come back. So some of the backscattered things still bounce around in this activation volume, and you get a broad range of energies that's counted as backscatter. We get our Auger electrons in the middle. Those are things, actually, you know what, I do want to mention a couple. Okay, yeah, we want to do this first. While we're talking about backscattered electrons, the most massive elements do the most easy job of backscattering. Okay? This is a plot of backscattered electrons normalized to total electrons and a plot of energy. So what do we see here? We have 5 elements: carbon, aluminum, copper, silver, and gold. With gold in the green, we have the highest yield of backscattered electrons and the highest fraction of the input energy comes back as backscattered electrons. In other words, gold or high mass elements are very efficient at producing backscattered electrons. As our material goes down in mass, in Z number, I should say specifically, we get less of a backscatter signal, but we also have it penetrate further into the sample. Because gold, or something that's heavy, is rather efficient at generating a backscatter signal. So, what does this mean for something that's carbon or aluminum or a silicate? The depth of electron penetration is also a function of the material. If something has a high Z number, it keeps the electrons close to the surface and backscatters them out very quickly. If something has a lower Z number, the activation volume for the electrons going in is larger. We had a gold-coated sample in the room. Why is it difficult to get backscatter signal out of a gold-coated sample, even if the gold is only tens of nanometers thick? Because high mass elements like gold are extremely efficient at producing a backscatter signal. So even though we're penetrating the gold with some of our electrons, the gold, compared to carbon at the same thickness, is far more efficient at generating a backscatter signal.
Is that enough for if you wanted to see backscatter electrons in clear sample in gold? I could see, and really, I mean, a little bit. You can see, right? It depends on the phase differences, right? The average CD, the comment, but no, they were my image. I can get it all, like 10. So why do people code it?
Because you don't usually use it on an SEM, first of all. Second of all, if you are dealing with a light element like carbon and you have significant charging, BP back there, well, can I carbon coat my carbon? And, you know, I can, but it's going to interfere with any signal from the thing I care about. So it might be that on BP's samples, they may at some point try carbon or gold coating them. Because, okay, maybe if we're contaminating carbon with carbon, my EDS analysis is going to be carbon from both sources, and I have no idea. If I really want to get something that is an EDS or microprobe analysis, and I've got an SEM that's available to do this, I might have a better job if I have it gold coated. Because if I had a gold coated version of their sample, maybe my activation volume will be enough that if I just subtract out the gold signal, everything else will actually be the atomic ratio there. The other answer to that question is that there are analysis types that very much prefer gold coats, such as SEMS. Secondary ion mass spectrometry often uses gold coats rather than carbon coats as the strongly conductive thing that they can get out of the way. And if they're not analyzing gold or any element like that, that is what is often preferred in those labs. And if you want details about that, I am not a SIMS person, so I cannot give you any further details than that. I don't know what the vaporization state is like for copper, frankly. I don't know. It might be something you would be worth trying, but I don't know how to vaporize everything. So. Okay, everybody got the point on that slide? Okay. While we're thinking about penetration into the sample, we should come back to accelerating voltage. Because at higher accelerating voltages, the samples penetrate, or the electrons penetrate more deeply into a sample. Means that if you're looking at surface features or a coating on the surface, your accelerating voltage plays into your ability to see that. All you do is turn up the accelerating voltage, you are minimizing the effective surface feature. So here on the left is, on a similar microscope to the one we have here, a low voltage image and a high voltage image. If we are looking at this one, in the low voltage image, surface features are becoming more obvious. In the image at the right, surface features are becoming less obvious because the electrons are penetrating deeper into the sample. Higher voltages will offer you the trade-off of making heavier elements visible. So if you're, if this was a gold spot on the surface of these glass beads, higher accelerating voltage might make that more visible. But in the case that it's not, the accelerating voltage here is making things fluoresce from deeper into the sample. So I don't remember if I mentioned that when, I think it was BP, where it was one of you two in the corner asked earlier, what's the trade-off for accelerating voltage? There's another version of that. So we're thinking now about exactly what's going on in the activation volume. This is another part of that. Other stuff that we haven't covered in terms of secondary electrons. Well, here's the full plot of electrons generated under electron bombardment again. The cutoff for what's a secondary electron is somewhat arbitrary. It is 50 electron volts. It's in the middle of the area where very few electrons are generated, but not zero. It is effective. So there are quite a few more electrons generated that scatter elastically up there, and the inelastic ones are the low energy ones. You kind of pick an arbitrary dividing line in there. How does a secondary electron detector work? That is this plot. This is an Everhart Thornley secondary electron detector. You generate your secondary electrons at the sample. They are drawn into the secondary electron detector placed off to the side by an applied magnetic field. It then basically goes into an electron multiplier. And we've mentioned those before because they're useful in things. An electron multiplier is one electron hits a charged plate. Because the plate is already charged, that releases 5 electrons. Each of those hits the next charged plate, which each releases 5 more electrons. Now it's 25. Now it's 25 times, it's 125. and it goes through a set of plates to generate a much more increased measurable signal. This is what is happening in the secondary detector. Why is this different from the backscatter detector? Because when these two electrons come in, which one generates a stronger electrical signal? This one, because its voltage is already higher, it has more power to it. So we can use a different detector design for a backscatter detector versus a secondary detector. The secondary detector, we have to turn up the energy somehow to be able to turn our signal into a detectable current. So the rule is the electron strikes the thing, causing it to emit light. That light passes through a quartz window, maintaining a vacuum. That light is conducted to a photomultiplier that increases the signal. That signal is converted back to an electrical signal by a photocathode. The electron multiplier increases the signal again. And finally, the output is recorded by a Faraday cup. This will be on the quiz later. Okay, is this worth knowing as part of the basic lecture? All right, fine, it's not. This is what's actually happening in the secondary electron detector because they're low energy. The high energy electrons, the backscattered electrons, have enough energy to excite the detector on their own. Low energy electrons do not. So you apply a large positive potential to draw the electrons in and cause a cascade that builds up to a signal that's detectable. Applying this large voltage inside the electron microscope cage would actually affect the entire cage if you didn't wrap a Faraday cage around the thing to keep the voltage inside of that box you put it in. So the design for your two detectors is somewhat different. I go all the way back to wherever I showed the last one. Okay. Our secondary detector and our backscatter detector are two actual different beasts because of the different energies required for each of them. You have heard me call secondary electrons SE2. Why the hell have I called them SE2? Because there are 4 types of secondary electrons generated by bombarding stuff with electrons inside of an SEM. Anytime an electron finds an atom, it can dislodge a secondary electron. This happens throughout your column. SE1 is secondary electrons generated very close to the interaction surface volume. Okay. SE2 are generated somewhere inside of the analysis volume that you're activating with your electron beam. SE3 are generated elsewhere inside the sample chamber. Did the color just change with that lens on it? Yeah. I think that was me leaning on the thing. All right, so SE3 are generated throughout the sample chamber. Okay? And SE4 are generated by electrons that hit the final aperture and then bounce back to the electron detector. So, if you ever are on an SEM and see it listed as an SE2 detector, that's first of all why it's called an SE2 detector. Your secondary electron detector is placed off to the side for a good reason. Because if here's your backscatter detector, your backscatter detector is close to the gun. The backscattered electrons are generating a secondary electron signal throughout this zone. So we're trying to draw in the secondary electron signal from here, where our sample is, Other places that interact with backscattered electrons will generate their own signal. If you put the Faraday cage off to the side and put your detector off the side, most of the high energy backscattered electrons don't get pulled in. Only a few do, and they don't overwhelm the signal. So there is enough secondary electron generation elsewhere that if it wasn't designed this way, you couldn't get a secondary electron image, which is kind of cool to think through. As you've seen in an SEM image, when you have it actively scanning, there's always a little bit of noise, right? Why is there a little bit of noise? Because both your backscattered and secondary electrons are in fact bouncing around your electron sample, your sample chamber the whole time. And occasionally they bounce off the wrong wall and come back to your detector. Thus, noise is always something that exists in an electron microscope. So, how do you minimize this? Well, you consider where your signal is. You consider your voltage if need be, okay? You also just collect for longer. When you're collecting an electron microscope image, you make sure you image for long enough that noise is overwhelmed. I can take a sample of the yesterday. I don't really care about it. Was it mine? Yes, those were mine. Okay. Yeah, you can take those with. If you ever publish anything about it, and you know when you're a grad student, you are required to include me as an author. Deal? All right. Also worth noting, this arrangement does create directionality. So in your sample, in secondary electron imaging, your detector position is off to the side, so there's always going to be one side of the secondary electron detector that's favored, one side that's hurt a little bit. This is fun. This is an in-lens detector. In this position, the magnetic field of the objective lens right here is used to select and accelerate your secondary electrons into the detector position. I have used a SEM before that has both a standard secondary electron detector and an in-lens detector, where change the position of the detector, and this can reduce interference from some of those other electrons. Our backscattered electron position detector is something like this. I believe the secondary detector is in fact still off to the side. So there are engineering tools that can manage some things, like dealing with SE3 as a noise source. All right. So now that we went through that again, what type of image are we looking at? This is a secondary image because many of the edges of things are being lit up and the texture is being lit up. Type of image is this. Ceiling just click at me?
Is it a different? Is it?
Same material.
Oh, okay. I didn't see it.
Nope, this is actually the backscattered image on this zone. Okay. This is a truly mixed image where we have assigned secondary to one type and backscattered to another type. There's many ways to mix these things. This is a calcified particle in cardiac tissue. I like this as an example of both backscatter and SE2. Question in the back or just scratching the face? Cool. Right. So that is my additional stuff on SEM operations that is excessive and boring and includes details of vacuum design that is my Friday afternoon and the week stuff on that. Next on the list is a couple of additional SEM techniques to familiarize yourselves with. Before I get to that, pause for questions or additional discussion. BP. Ours calls them topo. Topo is sort of doing that. How else could you do a combined image? Well, you could always collect a secondary electron image and a backscattered image of the same area and use a digital processing tool that turns one black and white image into one color and another black and white image into another color and combine them digitally. Are you familiar with any image processing tools that could do this? You've gotten two in the last day. ImageJ can do this, and XMap tools, although you have to coax it a little bit, can do this as well. And sometimes that's actually really useful. Be able to turn one into one color and the other into another color, because our eyes do color imaging a lot better in some ways than they do grayscale. Anybody else? Go for it.
The image of the activation, how do you get the image of?
Basically, literally, you're firing an electron beam at plastic, so you're damaging the plastic during the analysis. You pull the plastic out, and you cut through it, and then you use some tool to image the plastic, the area that you've damaged. Like this is how when I showed the diagram of the electron activation zone that was this slide in the first class. That's actually how we know this, and that's throwing in the additional details of what does current do to this, what does accelerating voltage do to that. That is stuff that was tested back in the 60s. Once they found that there were some materials that you could use to do this, that basically under electron bombardment vaporized. So I cannot tell you if that is an electron microscope image of the electron microscope damage. It might be some other type of camera. I'm not certain. All right, continuing with our list of techniques. Now, I've got what, 1, 2, 3, at least 3 more techniques that are on my list as things you can do with an electron microscope that you're going to leave here with a basic understanding of, but you're not going to do them here because frankly we don't have them, and quite simply learning what each of them is a whole 2-day course anyway. So it's an advanced SEM technique or a modern SEM techniques course. You're going to leave knowing these techniques. You're not going to leave knowing how to do them. If you need to do them, you talk to your lab manager and they will sit with you the first couple of times you do that after you prep the sample. Cathodoluminescence is first on the list. You take an electron beam, you fire it at certain elements, and in the process of the electrons scattering and bouncing off everything and energizing stuff, you pump some electrons up into orbitals that when they return to their ground state, they release visible light. In other words, you fire an electron beam at your material and you get it to glow. The actual rule for that is, okay, secondary electron passes an atom with approximately 3 times the energy of the transition associated with visible light. That's roughly what it takes to excite that. So it's a secondary electron passing through something and it loses some of its energy to bump another electron up an orbital. And if it's about, okay, quantum mechanics again. All right. The release of that energy generates cathodoluminescence. So under electron bombardment, when you have the right type of element present, where it can do this transition and give off light in the visible, sometimes it happens. There's many types of materials this works on. In a geologic or planetary sense, this is what we do zircons on. Why is this done on zircons? Because the elements that probably do this in zircons are the rare earth elements and trace elements that substitute into the zircon structure. Those are the ones that glow. And that means you're getting a measurement of the abundance of trace elements in any band of zircon growth. Since zircon is truly forever, unlike diamonds, we're going to use, it's a geology building, right? All right. Zircon is truly forever. It does not have significant diffusion of heavy elements substituted in there, which means 4 billion years later, you can still recognize growth banding in these things if they have not been turned into dust by radioactive decay. So cathodoluminescence is often used on zircons because you can recognize the growth band. If I just gave you this crystal, you would not necessarily know where the core of this crystal was if you wanted to analyze it for the oldest age possible, or if you were trying to map out the growth of it. Using cathodoluminescence, you can say, oh yeah, it grew outward from here and then grew in this direction. If you just targeted the center of your grain and said, I'm going to measure the center of the grain to get the age, you're going to get some portion of the oldest stuff and some portion of younger stuff. So zircon, this is very often done before you gold coat the thing or sputter coat the thing for isotope analysis. That is another modern SEM technique tool. Basically, all you need for this is a visible light camera. So it's actually not, you can set up a cathodoluminescence unit on an SEM rather easily. All right, we've covered Auger electrons. Okay, we mentioned that the other time. All right. What happens if your material is not flat, but has edges to it and shapes to it? What happens if you throw a crystal that has crystal shapes into your SEM? Well, we can't do this in ours without Play-Doh, but there are many SEMs that are built such that these stages can actively tilt. This can allow you to, if you have a crystal with a crystal shape to it, analyze one face, tilt it, analyze the next face, or even be able to do things like measure the angle between faces. Also, as we've seen, the secondary electron detector is off axis. So maybe if I want to eliminate some of the secondary electron bias from one side, I tilt my sample toward that detector, and this enables me to get a better secondary electron image. Modern SEMs often are built with tilt corrections, where digitally you can tilt your stage and then begin to do some amount of balancing out and correcting for the tilt, or setting the focus so that it adjusts for it as you tilt this. These are settings on some modern SEMs. You're not going to see them here, but you might see this on a field emission scope. Because an SEM is not actually taking a photo. It is only collecting digital data. Digital data can be processed digitally, which means that if your sample is tilted, you can apply a digital correction of some amount to deal with it by telling it this is a tilted sample and I want to apply a digital correction of X amount. Now that we can tilt our sample, it's time for this critter. All right, who's familiar with this? Little bit? All right. Electron backscatter diffraction. Yes.
Just saying,
Hop in.
if anyone, so something's done, so if anyone else wants time on this.
All right. This is the one that if we had a field emission system in this building, I would this would probably be a 5-day course, and we would have spent a day on this. We do not have this in this building, so we're not doing that. But this is perhaps the last major modern SEM technique that is applied broadly that is worth spending time and understanding. It has two super powerful uses. It can uniquely identify solid materials by unique measurement of their atomic structure. And you can identify orientation of things in three-dimensional space. How would you do this? Well, all right. You start with a highly polished sample. Because we're doing atomic structure, that layer at the surface of damaged and strained material from sample processing will affect this. The more you minimize that layer, the more effective this is. This is where those high quality sample processing techniques come in handy. You tilt your sample to about 70 degrees. So here is our SAMP electron gun that is generating an X-ray response. Here is our EDS detector. We move an analysis screen, a scintillator, into position horizontally so that we have a sample that's at 70 degrees and it's tilted relative to the gun and relative to this detector. Bragg's law. I believe that the equation for this of n lambda equals 2d sine theta is actually on his tombstone. Okay, I believe you can find that. Okay, so what is Bragg's law? This is the key to X-ray diffraction. The rule is if I have X-rays coming in with some wavelength, well, those X-rays will come in with some wavelength depending on the spacing between atomic layers. The X-rays will bounce off layers in an atom, and either they will bounce off constructively so that their positions of the peaks and troughs are lining up, or they will bounce off destructively where the peaks are canceling each other out. The exact condition where they bounce off constructively is a function of some integer, the wavelength of the X-ray, the angle that things are coming in with, and the spacing between the atoms. So let's say I know the X-ray wavelength and I know the angle that I'm shooting X-rays in. I can now solve for the spacing between atoms. Thus, I actually know the spacing between two layers of atoms in my mineral uniquely by this technique. And I can change, if I have well-collimated X-rays, the angle of the analysis or sweep through X angles to be able to see which angles produce positive responses and use that as my measurement of atomic spacing. That is my 2-minute basics description of X-ray diffraction. It is perhaps the most powerful tool in mineralogy because uniquely identifying mineral spacings allows you to identify the symmetry group and atomic spacing of your material uniquely. So much so that using this, I can even identify different versions of two materials. I can identify forsterite versus phthalate because the change between iron and magnesium in solid solution changes the structure enough that I can measure a difference in the atomic spacing as a function of chemistry. So yeah, here's the Bragg condition. This one is them interfering constructively so that we have one beam comes in, hits this layer, one beam comes in, hits this layer, the two peaks come off, the two troughs come off together, so we get a strong signal. This is them interfering destructively, peak and trough coming off together. Then they interfere destructively and you get no response. It is a very clear pattern. It requires you to know your X-ray spacing, and it requires you to know the angle that you're shooting things at. In single crystal X-ray diffraction, you literally take your crystal, spin it around by hand, in a machine that's firing X-rays at it, and this will analyze along the different axes the spacing of the atoms and allow you to uniquely identify the X-ray structure. These are powdered X-ray signals down here, which is in fact, we have one of these that's been rolling on Mars for more than 10 years now. The Curiosity rover has one of these on it as a mineral identification tool. In powdered XRD, you conduct a single analysis where you vary the angle. And as you're varying the angle by sweeping your detector across the powder, you get strong spacings and weak spacings that show up as single peaks that you can use as identifiers for certain symmetry planes in your mineral. All right, now we're going to do this in an SEM. Electrons have a wavelength. So anything that has a wavelength can do that same equation. Now, you may go back to your high energy. I don't know if that was a Nobel Prize or not for de Broglie. That's the de Broglie wavelength, which is the wavelength of an electron. That's the, we're at the edge of quantum mechanics right here now, where the smaller something is, the more it has a wavelength, okay? The electron wavelength is typically small. So to do diffraction with electrons, you need a typically small angle. So what do you do for your sample? You tilt it until your angle is pretty small. Because now you're doing that same analysis. You tilt your sample steeply relative to gravity and then fire electrons at it from your gun so that your electrons are hitting your sample with an angle of something like 20 degrees. You generate your normal analysis volume. You generate your normal set of X-rays, except by going in at a small angle, you have also had some directions that meet the Bragg condition. And the electrons thus come in, bounce off that plane, and scatter outwards in cones from that. This creates bands of electrons that come out as this shape in the directions that satisfy the Bragg condition. With me so far? Okay, so now I stick a plane detector in here, and the cone of electrons that comes in hits that detector and gives me a line with some orientation in space. If I have a big enough database that turns patterns of these lines, or near lines, they are almost curved, they're slightly curved lines, into readings of what planes are generating them, I have the exact same information that I have in powder or single crystal X-ray diffraction. I have a direct measurement of atomic spacing done through diffraction. Those bands are called Kikuchi bands. This is an EBSD pattern. It is a very beautiful one. I love these. I just think these images are gorgeous. Okay? These are the patterns you get on that scintillator screen. And every one of these bands is some version of the reflection off of a plane. And the places where they intersect and their orientation, the pattern that's on this is characteristic of the mineral structure or material structure that is creating the pattern. Now, you will not win if you try to memorize these. This is another of those things that databases do. This information is the exact same information that is in a diffraction pattern conducted by single crystals. You are specifically and uniquely measuring atomic planes and atomic spacings. This information is sufficient that if you identify a new mineral with an electron microscope and you want to publish the structure of this mineral, this is sufficient to publish what the structure of the mineral is and the symmetry group for the mineral. Exactly as if you had a single crystal of a brand new mineral that you brought back from another world and you identified it by putting the single crystal in a single crystal diffractor. So you can measure and record the atomic spacings and full details of the structure in this. Unlike single crystal diffraction, where you need a crystal that you can hold with your hand, this can be done if your material is the size of an electron beam analysis volume. So if you have the tiniest bit of a mineral, you can identify the phase by measuring its chemistry via EDS and its structure via EBSD. And that analysis together can be sufficient to identify a micrometer-sized mineral in your sample. Does anyone know the most abundant mineral in the planet Earth?
In the earth.
In the Earth, period. Correct. It is called bridgmanite. It is a polymorph of olivine. When you take olivine to high enough pressures, you get the 660 kilometer deep discontinuity. Olivine converts into another polymorph. When I was in grad school, we called that material magnesium silicate perovskite because we had the structure of it. It was a perovskite structured mineral made of magnesium and silicon with some iron in it. We did not have a mineral name for it because it could not be, when you cannot bring it up stably from the lower mantle up to the surface, even in inclusions and stuff, it breaks down. It had never been found. The group at Caltech, using their field emission SEM, found shocked bridgmanite as an inclusion in a meteorite. Because it was a naturally occurring sample where they could measure the chemistry and measure the structure, that took it from being a thing that we know exists down there that we have no mineral name for it, into something where we could give it a mineral name. And they gave it the name bridgmanite after Percy Bridgman, who got his Nobel Prize, I think in 1960, for X-ray diffraction and crystallography. So mineral and phase identification is one tool in EBSD. The other thing is that if I spin this around, as I move my crystal around, these intersections will move around. So I don't just get the crystal shape, I get the crystal orientation in three-dimensional space. So let's say I produce a very finely polished sample, and then I do a map across my sample. I get the orientation of everything in my map that produces a strong signal. This is a pole figure. This is a map of crystal orientation in stuff. What types of analyses in geoscience do we care about the orientation of things? A good one is metamorphic petrology. Because in metamorphism, you have a strong force in one direction and a weak force in another direction, which will produce alignment of certain crystals. So you pull your sample out, you polish it, and you measure the orientation of your stuff, and then plot a figure where the orientation of those things are known. This particular band right here and this particular section right here are well-oriented bands here for whatever reason. I'll be honest, I picked the prettiest EBSD map I could find an image of. Okay, it was from literally ebsd.com. All right, okay. fine. Okay, they're just, like, they're gonna give me a good image, right? Okay. This is a real good use of this, because from the micro scale, I can now reconstruct the exact orientation of everything. And if I have more than one cycle of metamorphism, that might be recorded at the micro scale, or the exact orientation of strain directions, or in a shock sample. The orientation of things may very well record something about the shock direction or shock intensity, or how the waves propagated through things. Anything that has a directionality to it and leaves an orientation in crystals, that could come up with. Settling of things, settling of clay minerals, settling of crystal grains in a magma chamber. Anything that could produce some orientation is something that you might have reason to measure using EBSD. That is my EBSD section. Pause for questions on that as I take a sip of tea. To do that, actually consult your lab manager, because not every SEM has an EBSD. You need specific designs for it, and you need higher quality sample prep than what we can do here. At the very least, I would have needed to do vibrational polishing for a couple of hours on the samples I prepped for you folks to be able to do this. And that may not even be sufficient. We might have needed to, do another diamond powder step somewhere in there as well, because we go from, those little gaps. We can ignore those gaps on the SEM to all of a sudden those little gaps are areas that don't return signal or return a random signal and become problematic. And the LB layer that we talked about in the sample preparation lab. Well, now all of a sudden that tiny bit of strain that you impose by pressing down on the sample and grinding into it, that becomes a source of error in this measurement. So minimizing that through sample preparation is ideal. Although this class focuses on SEM, we also have most of what we need to understand TEM, transmission electron microscopy, in this class. In fact, TEM was developed 30 years before SEM because the detector design is simpler. You literally can run TEM with photographic film, which is you blast enough electrons at your sample for some of them to go through it, and you record what's on the other side. And if your sample's thin enough for electrons to make it through, boom, you've got a transmission electron microscopy image. So, transmission electron microscopy is, remember that analysis volume? Have your sample be that thin. And you will get some interaction of the beam and your sample, and then a signal that goes through the other side. Some amount of various things will happen as material goes through. Some amount of electrons will get absorbed by atoms that are there. Some will diffract in certain directions. Some will scatter elastically off of the nuclei. Some will scatter inelastically, creating secondary electrons again. So you get a lot of different analyses here. I'm not going to spend my time talking about every single one of them again, because you've now heard those. And for TEM, there's our own rules for that. Here's a TEM image of a bacillus cell. You can literally see all the little cilia and things on the edges. Okay. We do want to spend a second on, in addition to introing TEM, is STEM, or scanning transmission electron microscopy. Because it is possible, even on a SEM like the desktop ones here, to buy a tool that would allow you to do this. What would you need to do this? You would need a detector that goes at the bottom of the stage. With sufficient sample prep and a thin enough sample, you would then have the ability to do this. So in SEM, we've covered what that is. In TEM, we basically blast our beam through the sample, and we have a detector that's over here. In STEM, we're doing like we do in scanning electron microscopy, and focusing our beam at a single spot on the sample, except we also have a detector down here to detect any signal that comes through it. If your sample is a wedge that's a centimeter thick, you will not get a signal through it. But if you put a thin section on there, you can get a whole bunch of detectable signals down there. There are some electrons that head straight through. There are some electrons that bounce off at certain angles and that are detectable in various positions. The ones that were in scanning transmission electron microscopy are labeled as bright field, dark field, and high annular dark field. Acronym wear out, okay? Bright field is stuff that travels directly through your sample. It is interacting with the light elements and not scattering much. A dark field signal is stuff that has interacted with higher mass elements and been scattered off this way. And the HAADF are things that reflect, that would scatter off truly high mass nuclei and spread out. So we're getting a detectable pattern that we can then turn into an image at each spot by recording the abundance of the bright field and dark field and HAADF electrons as we go through this. So just like scanning electron microscopy, we can then take an image of a certain abundance of electrons coming through and turn that into an image across the thing. So here is bright field and dark field imagery in scanning transmission electron microscopy. Okay, bright field stuff is where it's blocked here. This is getting blocked because this is a higher mass element. This material is not letting stuff go straight through it. It is scattering it off to the side. In this zone, you are seeing something that has higher mass than the surroundings. In the dark field, you're now able to see some of the details of this because the electrons that were blocked over here are coming in at the dark field image. I believe, if I read correctly, this is some version of a clay. So you're looking at a single clay grain in there on some sort of probably organic background. And so where you see the pattern in dark field, you're looking at something that is literally bonded to that clay. That I do not have a good answer for, because I am not a TEM expert. That is a good question for a TEM expert. TEMs are not cheap. Okay? To turn ours into a STEM would literally require the right sample holder. To get a TEM here would require a $2 million vacuum powered instrument. So, there's always some benefits to being able to analyze through things and to be able to see through things. And if I have, let's go with this example. Let's say I have a clay mineral. I have organic compounds inside of my clay mineral. I can't see those with an SEM. A TEM can see those, but that's a lot of sample prep to do it and a $2 million machine for a TEM. So if I can add an STEM, and a clay mineral is basically already thin enough that if I can put it on a grating, it's going to go through it. Well, now I can look for the tiny bit of organic matter or whatever else is stuck in there in between layers of this clay mineral and be able to characterize their size, shape, and their depth through the thing. Just as coming up with, based on the image, I was able to track down a plausible example off the top of my head. Fields. How many techniques am I up to yet? Is this four or five? All right. Electron energy loss spectroscopy. Okay. You pass a beam through your sample, as in STEM or TEM. Some energy from the beam is lost because of inelastic behavior. Most of the energy still goes through, but some is lost because the beam interacts with some of the surroundings. So if I am the detector and there's an electron beam being shot through, this main peak right here is the beam that's going straight through. These other peaks just off to the side are electrons that have just lost a tiny bit of energy, but they've lost that tiny bit of energy by interacting with my sample. This is another thing I could technically measure. How much energy has been lost to the material? This can be correlated to ionizations of atoms in certain ways, as well as vibrational shifts. Because one of the things that we could be setting off is a molecular vibration. What do we use molecular vibrations for? Well, that is infrared spectroscopy or Raman spectroscopy, meaning that can be used to identify compounds. So if BP wants to go nuts, and I mean absolutely bleeping nuts, you could, if we're trying to figure out what some carbon-bearing compound is, eels is an option. You clearly need specialized equipment for this because we're not just doing STEM, we're building a detector that can specifically measure the peaks associated with electrons that have lost a little bit of energy. So we've got some work to do in our construction. These are specialized instruments, but it is another thing that exists coming out of the scanning electron microscope design. I'm going to go drink first before I answer this. Short answer is I don't know, and I'm going to blame the physicists. Is that fair? Because, I happen to be a geochemist, and you have hit the edge of my knowledge. This is one of those things to go to Wikipedia and Google for. And don't trust the AI results. They will probably tell you that it is something related to plasma, because it won't. Yeah, good luck. Okay. All right, we've actually thought through a little bit of thin film analysis here because we had a gold-coated sample, and so we were forced to kind of think through what happens if you have one film on top of another. Numerous industrial processes use very thin films of one thing precipitated on top of another. That could just be constructing a mirror. That could be something as complicated as layers on top of a solar cell, where one element is collecting the energy and another element is processing it as a semiconductor, and then another element is turning it into an electrical signal. And you literally have like 3 different coated layers on top of this. So numerous industrial processes use thin films. Now that we've seen what our analysis volume looks like, if we have some understanding of our analysis volume on a material, we can do that or use that as a way to measure things like the structure or thickness of our thin film. Well, this is a thin film that's been turned on its side so we can measure it in an SEM. But let's say that we wanted to measure the thickness of this layer in a very quick, dirty operation. And I had 5 different samples of this, and I wanted to see which one was thicker. An EDS analysis, qualitatively, can tell me which one is thicker because, well, if I have the same substrate beneath them, and I have a gold layer that varies in its thickness, the EDS analysis of composition will be a measurement of how thick my layer is. Same thing with the backscatter image. If I had 5 different layers next to each other, the backscatter contrast will be a function of the thickness of a layer. So here is an EDS spectra of a thin film deposited at 750 C and annealed under an oxygen pressure. I don't know exactly why on earth they were doing this. This is material science applications, but they are material science applications of an SEM. Thin film analysis is thus the final, I think, thing on my list of advanced SEM techniques to cover in this course. I think the last slides, yeah, this is not a simple problem. So because, as we saw, penetration depth is affected by the type of material, you can't simply unmix EDS peaks into composition because the analysis volume changes as your thin film changes. The good news is, guess what? Again, there's software built to do this. So if you need to, these are examples of tools that have been developed where you can find software to unmix things. We also have particle size analysis. In fact, our SEM can do this. We just don't own the license to the software that does this because nobody does it. If you have a need for an SEM to do particle size analysis across a sample, we can do the same basic thing, take a bunch of images. We just need to go to nanoscience and buy the license. So if you want to put in a proposal to do that here, great, we'll just buy the license for it. And I think that just takes me to my EDS slides again, which is where we finish up, and we've already covered that. That is the end of my advanced and rambling section on all the other things you can do on an SEM, and also demonstrating why you can't just do that on every single SEM, because boy, every one of those has gotten specialized now. The most general of them is probably EBSD, which is why we probably spent the most time on that. But yeah, they all pop out of detailed understanding of how the system works. And that's all I got. I hope you all had fun. Questions, comments, angry rants? You want to go put a croissant on the SEM and see what it does? I'm actually kind of curious.
You find a little bug. And subjective. I think it would be the experience electron.
Go for it.
If we want to come back to you, there might be beneficial. Have to do that.
Email me. In fact, we have one of our postdocs is right now is who is an SEM user, started here by taking this SEM training course last year and realized, oh, you mean there's postdoc options? I might as well apply for one of those, with the plan of I'm going to come and use the electron microscope on some of the meteorite material that I've wanted to look at for a while, and that was their research plan. They are now here as a postdoc. So yeah, if you or your lab group want SEM time on this machine, it will take an hour to retrain you once you get back here. If it's 6 months from now or whatever, and not next week. And after that hour, you'll basically be turned loose, and I'll have to find a time to let you into the building or something like that, or arrange with Claudia to let you into the building or whatever.
If anyone the need for an SEM Dallas, the one at UT that I'll be helping other people work on is free. So y'all can email me as well, and I think free time on it. Mm-hmm. It's not like the best SEM, but it does a really good job, and it's also like no one's ever used gloves to touch that thing, so it's not the cleanest. But what do you think it's great?
What kind of materials do you do?
I've used it just to look at a couple of samples, like little chips of rocks. Okay. We have people all over the school come to use it because we're the free one. If you want time of the one in the clean room, you have to get training and spend hundreds of dollars.
Yeah, if a lab has bought a desktop SEM, they will often just have a desktop SEM that people can use. If y'all want to go track down either Willie or Serena to say see ya, they are probably hanging out down by the SEM. At least Willie is. If you want to continue using the SEM, that is it for the course portion. That is everything I prepped. And if you are done and you want to call it a day or call it a week, that is the end of this training course. If you don't want to go look at anything else, so you may use the rest of your time however you wish.
Yeah, thank you very much.
Thank you for attending.
Start taking us to completely fill out the. I'll never leave a box in. These are nice workshops.
This is the first workshop I've attended, so it is the best workshop. So you can let that TV go however you like.
I feel like I can much more confidently go back to my material science department and like actually know what people are talking about.
Yeah, I would be like the students from our last year.
Yeah.
They literally got thrown into the SEM. And then let go.
Yeah. Brian, how do things work with perhaps sharing these slides
Okay.
with
Uh,
my lab?
With your lab group, you are encouraged to do so. Okay. Should you decide to put this on your own website or something like that, there is copyrighted material in here, including stuff that has come from published papers and published textbooks. We have, I think, at least tried to, I don't know if it's fully up yet. We're trying to put last year's presentation of this stuff up as shareable content, which has required for stuff that is not from Wikipedia, actually contacting the publishers to verify permission to do so. So should you choose to publish this material on your own, you're without, putting a reasonable effort in to get all of the permissions from every publisher, you would put yourself at risk of a copyright violation. However, amongst your own lab group for educational use only, you would fall under the educational and fair use exemption, where you are simply getting content for educational use and distributing it amongst yourselves, which is literally the definition of the educational exemption for copyright law. And we do encourage that. So, in fact, one of the survey questions that they may ask you in the later survey is, have you used any of this material as educational materials for anyone else in your lab group or anyone else in your school? Which we encourage, as long as you don't, try to publish this on your own website to get clicks to your own website, because then you're stealing clicks from the person who published the material originally. Use the SEM. Take it with you if you're heading down to the SEM. It's a big library.
Okay.
That way you've got it with you, and if they lock the door at 5:15 p.m. or something, you don't have to scramble and find somebody else who's in the building. You just know where your stuff is.
Do you want me to take the Uber just with you guys?
If you do not want to take it with you, I can guarantee you it will find a home.
Good enough. Thank you.
If you want to take stuff with you, take stuff with you. Yes. I'm Jay Volta at LPI at USRA at EDU. They specifically don't give us your email addresses until they don't even unmask your name until well after until basically I could have gotten them last week, I think, because we actually knew who was going to be here then.
Yeah.
But we don't even unmask. They don't unmask names to the people who are on the selection committee until literally we know who's actually coming and that, you know, all of the alternates have had a chance to be asked if they want to come or not, and needed and so on. Like they were very, when they put the proposal in, they were very specific that we were going to do a blind selection based on merit associated with the application. And not based on, we're gonna admit our friends, so, yeah, I had no clue who I was selecting. So, and, yeah, I don't know that they would even give me a list of emails of the attendees if I asked for it. Yes,
We have a simple folder like that, and I avoid carbon tip at the bottom of this repository.
yes, you could. Okay, so the other thing for this, I don't know if it's the correct size or not, but these bolts are literally designed, so you screw them out on the right size thing. And probably this is a 1-inch round, if I'm seeing this right. Basically, like, assuming this is the right scale, whoops, it should literally be, you put your sample in there and you screw the bolts into the side of it, and those bolts do the job of the carbon tape.
So, I have one more question. Just the feasibility of your evaluation on the feasibility of using BDS as a preliminary analysis of carbon in a sample.
It's iffy. You can do it for the presence of it, and you know, do I need quantitative abundance on carbon? Very challenging.
It's not so common, just to see if there is.
If there is carbon presence or not, it's feasible. As long as your sample is not carbon coded, you can look for the presence or absence of a carbon beam in a map analysis, for example, and that will give you, do I have non-zero carbon in this area? Okay.
And so I can find the carbon-rich area relatively.
Relatively
carbon-bearing-
carbon rich.
Yeah, carbon-bearing area, then I can identify those areas, I can use Raman to identify the.
Yes, that could be a potential way to make that work. Keep going.
Is there a mailbox around, yeah, should be a mailbox, I want to mail this postcard.
That is actually the hardest question I have here. I don't know where to drop, I've never dropped mail out in this building, honestly. There is if you drive past the Ace Hardware, there is a postal office box in the Ace Hardware. So it's an actual, walk into the Ace Hardware, walk to the back edge of the store, look for a big sign that says U.S. Postal Service. That is, when I have to mail something here, I go to the Ace Hardware because it's in the post office's hands there. They have a postal office service station there.
Thank you.
Brian, for the samples that I shared on those, if you're, I don't know, if I wanted to take them with me, is there anything I can do? Yeah.
Okay, I can't, the one problem I would have is I can't easily give you something as a holder for them because we don't own any,
Okay.
okay? But I could give you a little sample box and nobody's gonna miss those. We have some of those up there. They will bounce around in there.
Okay.
Like the true ideal, if we owned any, which we don't,
Yeah.
is something where you actually insert the backside in and then put a cover on it. And those we don't have.
Okay.
So,
I wanted to test them.
thanks.
I didn't think to bring them.
All right, so what you could certainly do is throw a Kim wipe or two inside of a sample box and use that as padding
Okay.
and hope the best.
I mean, the other option I thought of is just not, I mean, I still have powder, so I could take new samples. So,
I mean, I'd try to take it with,
Okay.
you know, if you want a couple of sample boxes, I can go upstairs and grab you a couple of those.
okay, yeah, if you wouldn't mind, that would.
I will meet you down by the SEM since you're heading that way. I have to be up here a little bit and stop recording and stop sharing my screen and so on.
Okay.
Plug everything back in. And, yeah, I'll be down there in a couple of minutes, okay?